Well, hello everyone. Let's. I'll hope I'll make this short and sweet, straight to the point. Before I get started, how many here have used Kubernetes before? Oh, a lot. Oh my God, this is the first time I see so many hands about the question of how many people use Kubernetes. Okay, how many of you like YAML? Just out of curiosity. Ah, okay, I'm not the only one. I thought I was a weirdo. Okay, cool, awesome. All right, so let's get started. The talk is really focused on one particular introduction of a feature that was added to Kubernetes 127 that hopefully will make pod resizing easier in Kubernetes. And I'm going to also touch a little bit on the future of what that thing looks like. But before we get started, let's go into the basics. So resource management in Kubernetes. I think you have all done this. You probably have all seen it. But you have all seen something like this, right? Like a pod definition that has a resource request and limits, right? So that essentially tells Kubernetes on the request side how much slice of a node to set for a particular pod to run, and on the limit side how much to allow that pod to scale up to, right? So requests are basically set by the kubelet. One thing also to keep one quick thing to keep in mind is if you have a node that has 2 CPUs, it doesn't necessarily mean that all these 2 CPUs will be usable by your workloads. Usually Kubernetes itself will reserve part of that for system components. So things that run inside the system, the kube system namespace, but run on top of the node, kubelet, if there is any daemon sets, if you have any system critical things. So that's why when you do actually a kubectl describe on a node, you will have available resources and allocatable resources. The available resources is how much resources are available in the node total. And the allocatable is what's available minus what's reserved by Kubernetes. And the allocatable is the part that this gets allocated from. So when you set a request, then Kubernetes will take that allocatable, take a slice of it, and then guarantee that pod that those requests resources will be available. If there is no node that has this amount of requests available, the pod will be stuck in pending, waiting for a node to be available. And then the limits obviously will limit how much the container can consume, right? One thing that was introduced actually in 1.34, which is the last version, which came out in August, is they actually introduced pod level resource requests and limits. In the current model, requests and limits are set at the container level. So what the pod will, what Kubernetes will do is that it will accumulate the resource requests across all the containers in the pod, and then calculate that to allocate the resources for the pod. But now we have resource requests and limits at the pod level, which then can be shared across the containers inside that particular pod, right? So this could be useful if you're running, and you can also mix and match both. So you can have pod level resources, and you can have also container level resources. Obviously, the total amount of the requests, the total amount of resources requested by the container or the containers in the pod cannot exceed the pod level resource requests, right? But this is very useful if you want to have some visibility into what the pod is doing. You can just look at the resource requests at the pod level. How does that actually translate under the hood? Basically, for CPU, this value, which is the 250, that translates into CPU shares. So how much time the pod can actually use the CPU across a unit of time. So if it's 256, that's basically 1/4 of a minute, right? And if it's memory, well, memory is obvious. It's just like a slice of the available memory on the node. So for CPU requests, that's essentially the value that you have input, 250 in this case. I mean, Kubernetes reasons in 1,000, but at the node level, it's 1,024 because it's a base 8 system. So a 250 milli CPU will translate into 256 shares of the CPU. And then the limits also will translate into how much overhead that pod or that container will be allowed to consume. The memory is translated in bytes, but it's pretty much available in megabytes in your container level. So how do you right-size a pod? You have basically 3 methodologies that you could use in Kubernetes. I call those quality of service, although Kubernetes doesn't formally recognize them as quality of service, but I call them quality of service. Guaranteed is essentially when you set your pod requests and limits to be the same. This essentially tells Kubernetes, set this amount of resources, and the node will guarantee that those amount of resources will be available for you. Burstable is when you don't set limits. you just have requests. Essentially, in this case, Kubernetes will allow you to burst or use up the resources on the node up to how much is available on that particular node. And then this effort is when you don't set anything. So if you don't set anything, then it's, Kubernetes will just run the pod, and then it will not guarantee that the resources are available. So basically, as you go from left to right, from the guaranteed to best effort, if there is no resource contention on the node, the best effort pods will be killed first, followed by the burstable, followed by the guaranteed. I have a very nice diagram to show this. So if a node pressure occurs, the best effort will go out first, then the burstable, then the guaranteed. So there is an example where we have a node with a 4 gigabytes total memory. We have a guaranteed pod that's set 1,000, so 1 gigabytes. So that's a pod that has resource requested limits being equal values, right? Then we have a pod that sets a resource request at 1,024, but doesn't set any limits. And it's bursting a little bit with a 1/4 of a gig of memory. Because all the white space that's empty available resources, Kubernetes will allow that pod to burst, right? If a new pod which has guaranteed resources comes in, then there is still some room in the node, and the pod can continue to burst up. If it bursts beyond what's available on the node, then that burstable pod will be killed first, right? And if there is another best effort pod on the node, that will be killed before even the burstable one, right? So the TLDR for this, the story to learn, is always at least set resource requests and limits to be equal if you want your pod to not be evicted. For CPU, what happens is usually is throttling, because CPU resources are compressible. So the pod will be throttled, it will be slowed down, and you will see it, obviously. If it's memory, the pod will be killed. So if the pod has a limit on memory and it exceeds its limits, it will be killed. If the pod runs with either burstable or best effort resource management, there is no more memory available on the node, the pod will be killed first. There is also something called priority at the pod level. I don't know if you know this, but the priority in the pod level allows you to define priority between pods. So the pods with the lowest priority will be always removed before the pods with the highest priority. This is something that a lot of people probably have in the room have used before for something. It's a technique in Kubernetes called balloon pods. So let's say you have cluster autoscaler enabled, which autoscales the underlying infrastructure, adds more nodes to the cluster if needed. And let's say hypothetically that your cloud provider that you're using is slow to scale up. What you want to do is you want to have enough capacity available in the node in case of a scale-up event. So what you do is you run your workload with a high priority, and then you run a bunch of dummy pods with a lower priority. Those dummy pods, to call them balloon pods, will guarantee that there is a bunch of nodes available because they are going to be running. But in case your higher priority workloads need to scale up, it will scale up first, and then the lower priority pods will be deleted, right? This is a very common thing that people do in cloud. Hopefully, not many of you do it because it's a bunch of waste of money, but it's a very common technique for guaranteeing fast autoscaling on Kubernetes. Now, what if there is a way to handle the resources dynamically, right? Well, that's essentially what in-place resource resize, IPPR as I call it, was introduced to do. Before Kubernetes 1.27, resizing a pod means you have to restart it. In Kubernetes 1.27, as an alpha feature, resizing CPU and memory without continuous restart was introduced, and now it's actually stable since 1.33. This basically means that now we have mutable resource requests and limits, so we can change them. And we added this resize policy, which allows you to define what happens when CPU gets resized and when memory gets resized. And the two values possible are either not required or restart. So you can set your pod to either not require a restart, or so you have the control, right? Before, by default, the policy, even if there was technically no policy, but the policy was restart the pod, right? And then also in the status field, you would also have the status. So if a pod is being resized, the status will say resize in progress. And then once the resize is done, it will say resize done, and it will tell you how much resize, so what's the resized resources have been to. Now, a question I get very often is what happens if you resize a pod, but there are no resources available for the node, right? Well, this pod will be stuck in progress indefinitely until it gets killed and moved to a pod that has that amount of resources. Resizing a pod live, just keep this in mind, it is mutable in the sense that you can change the values in the pod definition live, but it's not mutable inside Kubernetes itself. Which means if you have a pod which is running, and you send a request to resize it, and then that pod gets killed, and then rescheduled on a different node, it will be spun up with the previous amount of resources, not with the resize value, right? Because the changes that you are making them at the pod level. You're not touching etcd. etcd remains the source of truth inside Kubernetes, so whatever YAML you have submitted to Kubernetes, that's essentially what will stay there. So that's the source of truth. So if you have a cluster pod running with, let's say, 1 GB of memory, you do a kubectl patch, which I'm going to show you in a bit, to resize it to 2 GB, and then that pod gets killed. It will be created again with 1 GB, right? So let's see a very quick example. I have a very dummy pod here. It's just Nginx. Inside there is one container, and the container has 100 milli CPU and 128 GB of memory, and it has a limit of 200 CPU and 200 GB of memory. So I'm going to, I believe I have it running. I need to delete it first. No, it does. OK, good. So let's go ahead and apply it. So that will create my pod, which should be running anytime now. All right, it's running. Good. So I'm going to run 2 commands. One of them would be a JSON, like a get, and I'm getting the resources. So you see here, I have 100 milli CPU, 128 of memory, 200 milli CPU as limit, and 1 GB of memory. And what I'm going to do is I'm going to issue a kubectl patch command to patch this existing pod, to resize it. So I'm going to show you how that command looks like. So we're just patching the JSON, patch the pod, and I am changing the resources. And so I have to specify where the resources are. They're in the container called Nginx. I'm changing my resource request to 300 from, what was that, 100. And my memory to 512 from 128. And if everything goes well, I should see this update without the pod restarting. So if I issue this command, Kubernetes will tell me the pod was patched, and I have my resource requests. Where are they? Resource limits. I changed it to 200 now. How much did I put? Yes, it should be somewhere here. Oh, that didn't work. What? Oh, yeah, no. 250. No, that didn't work. Actually, that did not work. Why? Hold on a second. Which one did I put? Yeah, Nginx resizable, that's the one. Sub-resource resize, blah, blah, blah. And it should not restart, yeah. OK, I was testing this yesterday and it worked. I don't know what's happening today. Describe the pod. Describe pod. And if we go look at the resource requests, oh yeah, it was changed. That's funny. OK, well, here, you see it. It's 500 CPU as a limit. That's essentially what I issued in my patch command. 1 GB as a limit on the memory, 300 milli CPU on the CPU, and 512 on the memory. And if I scroll down to the status field of my pod, there should be here a status called restarts count. So I'm going to grep on that. And you can restarts? No, I think restart with capital R. Yep, I have a restart count set to 0. So the pod did not restart. It was just live resized, right? So this is the basic feature. This is available today in all basically Kubernetes clusters starting 127 in alpha or starting 133 in GA. Now, this feature, which allows us to resize pod live, creates a bunch of possibilities. And to use these possibilities, the community is actually already working on it. There is already a KEP, Kubernetes enhancement proposal, to implement something which I'm going to explain in a bit. What we could, so you're probably all familiar with this thing called Vertical Pod Autoscaler. Kubernetes has two autoscaler mechanisms for pods, horizontal pod autoscaler, vertical pod autoscaler. Horizontal pod autoscaler adds more replicas, vertical pod autoscaler resizes the pod. Vertical pod autoscaler today will restart the pod to resize it. When you are setting a VPA on a pod, you can actually set it in two different modes. One is called auto, and one is called none. I call that recommendation mode. So if you set VPA to auto, it will resize the pod, and it will restart it. If you set the VPA mode to none, it will not restart the pod, but it will update its own status with recommendations. So it will monitor the pod, and then if it sees that the pod needs to be resized, it's not going to resize it, but if you do a kubectl describe on that particular VPA object in the status field, it will tell you what's the recommendation and how much resources you should add to the pod. Right? We've been recommending to people to use this as a recommendation mode. It's kind of hacky because, well, I believe not, because you could actually query the API server and get a JSON output and then use that as a way to like make recommendations for resizing pods. But one thing that a lot of people who are doing serverless know is that most serverless platforms today on the cloud has something called CPU boost. CPU boost allows you to basically allocate more CPU time to the container while it's starting to speed up startup time. That's essentially what VPA is trying to do. The Vertical Pod Autoscaler project is trying to add a feature called CPU boost. It doesn't exist yet, but it's coming. Let me show you an example. So this is a demo that we did internally. I'm going to have to pause a bunch of times to explain to you what's going on. But this is a demo that we done internally. It's proof of concept that we done to just kind of emulate how CPU boost could help speed up the startup time. So you see four, basically, the screen is split in four. On the top, you have a deployment. In the bottom, you have a kubectl get pods on the pod itself. So this is a Spring Boot application using Spring Boot 3. On the third window, you have the resource requests and limits. And then in the bottom, we have metrics. So without any CPU boost, it will take roughly around 42 seconds for this pod to start, for the container to start. So this is without the boost. You will see there, at some point, it will hit 42, and then the pod will be flagged as ready, right? Now, with CPU boost, pay attention to the third window, because the third window will indicate, you will see the resource changes live. So we're already going to have a faster startup time, and then at some point, those values here will go down. So for now, we are running with, you saw it? We're running with 2 cores as a CPU request and 5 as a CPU limit. And then at some point, they will flip back to 200, 500, right? So what is this? This is essentially an operator that we wrote. Again, this is the proof of concept because the idea is that this will become part of upstream Kubernetes open source. It's an operator that we wrote that allows us to define a YAML file, target a pod, and then tell Kubernetes, give this pod more CPU time during the startup time. Yes?
Would you not get the same effect if you don't put in limits?
Yes, you would get the same effect, but there is no guarantees, because if the node doesn't have those resources available, then you wouldn't get the same effect. Because with CPU boost, the idea with CPU boost is that we take the pod as you have defined it, and before we even send it for scheduling, we change the resource requests. So the scheduler takes into account that this pod will require this amount of resources before it even starts. Is it clear? Right? Good. So that's a very good question. The question is, if you don't set limits, you will get the same, because then the pod will be allowed to burst into the resources available on the node. But the difference here is that without resource limits, there is no guarantee that the node will have those resources available. With CPU boost, we're able to change the resource requests before the pod even gets scheduled, so that the scheduler takes those resources into account before it finds a node. Make sense? Cool. So that's essentially this feature. So this is using our own, as I said, using our own, sorry. OK, That's the demo. That's actually my last slide. So this is using our own operator that we wrote as a proof of concept. The code is open source. It's on GitHub. I can show it to you if you want. I don't really recommend using it as in production, but we can actually look at it. So if you were wondering what that thing does, it's essentially this. This is like the Cube startup CPU boost proof of concept that we built, which again is not production ready. But this is how it looks like. We define a YAML file called startup CPU boost. We tell it which pod to target with the selector. And then we give it resource policy. And in the resource policy, we have a percentage increase. So here we're saying increase the CPU request by 50%. And then we have a condition. And in the condition, we say, do that up until something happened. In this particular case, do that up until the pod is flagged as ready. We can also do a time-based condition. CPU boost by 50% up until 60 seconds, for example, right? And so the idea is that this will become part of VPA, Vertical Pod Autoscaler. This is the actual proposal that is being made upstream. And this is what will become available upstream as part of the VPA API. If you go in the bottom, you see startup boost. That's essentially CPU value 3. So boost my CPU to 3 cores for 10 seconds, right? And then there is also a condition. You don't see it here, which is, well, no, sorry. The condition here is 10 seconds. You can also set do that until the pod is flagged as ready. So this allows you to balance giving the pod more resources during the startup time, which is important for some type of applications, especially Java applications, where they request more CPU at the startup because there is like a lot of things happening, and then the resources then will be taken back, and then the pod will go back to the normal resources it needs during its runtime. So you don't end up wasting too many resources because you want to make the application start up fast, and you don't end up also undersizing the container and having the application start up slow. As you can see in the video demo, we went from like 42 seconds to like 12 seconds with CPU boost. That's it. That's all I had. We have 7 minutes left. I don't know if you have any questions. Thank you so much. There is a question, yes. OK. So the question is, what if there are too many pods requesting boosting, but there isn't enough resources in the nodes, right? So there are a few. It's not a problem for the following reasons. Reason number one, Kubernetes has a pod churn rate. The pod churn rate is a value on the API server that tells the scheduler how many pods to schedule at a certain time. So it's not so. The question I think you're asking, the much bigger question, is what happens if I have, let's say, the worst case scenario. All my cluster dies, and then all the pods come up again, and they all request CPU boosting, right? That's not going to happen because the scheduler is not designed to schedule all the pods in one go. It has a churn rate, so it schedules them in batches. So that's number one, right? Number two, Kubernetes is a promise machine. So if the pods fail to be scheduled because there isn't not enough resources, they will just be put back in a queue up until resources are available, right? That's number two. Number three, hopefully you have cluster autoscaler enabled, which will look at the scheduling queue, look at how many pods are stuck in pending states, and then if there are a lot stuck in pending states, it will create nodes for them, right? So those are the three answers, I would say, to this particular question. Now, if you are running in a situation where your cluster is running like bare minimum with barely the right amount of resources, I think you're probably not doing resource management right, and you should think about it again. Yeah, but then the question back to you, or to challenge that point, is that you don't necessarily want to be in a situation where you're running like limits, because what if you have a sudden scale-out event, right? You want to have some buffer in the cluster anyway. So this allows you to use that buffer to speed up resource or to speed up pod starts, but not waste them because you're not going to use them later. Make sense? Yes?
Then if you do resizing, the new pod will be at the old size. Can you also do the resize at the deployment descriptor? And it won't restart the pod?
Yeah, so the recommendation is to don't do the resize as part of the, like I did, like kubectl patch. Just like resize the YAML file and reapply it. Because if you do that, then Kubernetes will not reschedule the pod, especially if the policies are set properly. If you apply the file, the pod is not going to change. Like it's not going to, it's not going to change. The pod will not be restarted. YAML will know, like Kubernetes will know, okay, this is the same resource definition of an existing pod, just with a different resource requests and limits. So don't do what I did, because what I did is the equivalent of like SSH into production and upload a bunch of, What I did is basically, you have a server running production, you're missing some dependencies, and you just upload them over SSH. Don't do that. Make sense? Yes?
So if you have like a robot who's kind of stuck in a restart loop,
Mm-hmm.
is there anything foreseen to not waste all that precious CPU time?
Sorry, you have a pod stuck in restart?
Yeah, it's like every half a minute it realizes, oh, I have missing config or something,
Uh-huh.
automatically restarts and tries to start up again.
Yeah, so that's, okay, so a misconfigured pod that restarts, and then each time it restarts, it gets CPU boosted. Yes, correct. However, Kubernetes is designed with like a back-off mechanism. If the pod keeps restarting multiple times, at some point it will just stop, and you have this like crash loop feedback, right? So there is a maximum number of times that the scheduler have a limit, or not the scheduler technically, but like Kubernetes has limits for how many times it will try to reconcile a pod. And at some point, eventually, it will just stop. That's why, for example, let's take an example here. Let me do this. So if I delete this pod, and then I go here and screw up this image name, so I'm just going to put like a dummy. This is an example, right? Dummy image name, right? Well, this is not example, because in this case, it's not even going to be created. But basically, what happens is that because that image doesn't exist, it will error with image pool. It will try multiple times, and at some point, it will just stop and give me like crash loop feedback, whatever that error is. Make sense? Yes?
Can have a side effect on the application. I mean, at the startup, you just look at the number of CPU they dispose, and then they are no more there. So, I mean, for the threads, for example, in Java, you can have a side effect on that.
This is a question I expected. I have to preface my answer by the fact that I'm not a Java developer, so I don't really know much about how Java works. However, yes, that might be a problem. If the application cannot dynamically use resources, it might be a problem. I think this might be a problem for JVM, like old version of JVM. The new version of JVM is actually container aware, so it knows like how dynamically to load how much resources are available inside the container. Old version of JVM, which could not actually know what's happening inside the container because it's not designed to run inside the container, that might be a problem. I don't know if this answers your question. I'm not 100% that expert on virtual threads and all that stuff. All right, I have 1 minute left. I hope this was, yes, one more question.
How it will respect the Java ergonomic? At startup, Java tries to calculate how many threads they need, for example, for JC garbage collector and so on and so on. If this resizing applying after Java process start or before,
That's a very good question. Another one that I cannot answer because I don't know. I don't know if Java recalculates the ergonomics dynamically when the pod is running. Does it do that? Does it recalculate the? No, it only does it during startup time. Then in this case, probably this is going to be useless for a JVM-based application. I would recommend this, for example, for like a native application like Graal, because that doesn't have a JVM, right?
Specify to the JVM what the resources are.
Yeah, but you specify the resources.
In arguments, you can override it.
Okay, there you go. There is your answer. I love that the audience answering each other. I don't have to do much work. I have 4 seconds left. Do you have another question?
I just want to learn that you can explicitly
All right. Thank you so much.